Yes, sir.
Good evening, sir.
Yes, sir. Good evening, sir.
Good evening, sir.
Hi, sir. Yes, ma'am. Good evening, ma'am.
Sir, shall we start, sir?
Sure, ma'am. Yes, ma'am. We can start, ma'am.
Venkatesh, sir, shall we start, sir?
Yes, madam. 1 minute, ma'am. Yeah. Yes. Yes. Good evening to all. This is the ADAL FDP online FDP, the emerging trends in optimal design of electric vehicle and hydrogen fuel cell vehicle for sustainable futures. Day 1 completed and day 2 today you have 2 sessions. Session 3 is handled by Dr. Surendra Reddy sir, Associate Professor, Hosong University, South Korea, and the second session is session 4 is handled by Dr. Deepa ma'am from School of Electrical Engineering from Amrita Bangalore. I hand over the session to I welcome Surendra sir, and I hand over the session to Sarmila ma'am. Yes, ma'am. Sarmila ma'am.
Thank you, sir.
Thank you.
Am I audible, sir? Good evening to all. It's my pleasure to welcome you all
Clear,
for the
ma'am.
session. Okay. I'm delighted to introduce our Dr. Surendra Reddy Shalkuti, who has warmly accepted our invitation to be a resource person for session 3 of our 6 days online FTP program. Dr. Surendra Reddy Shalkuti has been working with Usong University, Republic of Korea as an associate professor in the Department of Railroad and Electrical Engineering since April 2014. He received a PhD degree in Electrical Engineering from the Indian Institute of Technology, Delhi in 2013. He was a postdoctoral researcher at Harvard University, Washington, USA from 2013 to 2014. His research interests include power system restructuring issues, smart grid development with the integration of wind and solar photovoltaic energy sources, battery storage and electric vehicles, demand response, power system analysis and optimization, artificial intelligence and soft computing techniques application in power systems, and renewable energy. He has published 3 edited volumes with Springer and over 300 research articles in peer-reviewed international journals and conference proceedings. He served as guest editor for various international journals. He is also an editorial board member for many journals. He received the 2016 Distinguished Researchers Award from Usong University Educational Foundation, Republic of Korea, and the POSACO Power System Award 2013, India. He is listed in the top 2% of scientists published in a study conducted by researchers of ICSR Lab, Elsewhere, Stanford University, USA. He has Google Scholar citations of 7039 with an high index of 42 and an I10 index of 151. He is a member of IEEE and IEEE Power and Energy Society. We are honored to have Dr. Surendra Reddy Shalkuti as the resource person of today's session. Once again, I welcome you, sir, to handle the session in the topic of design of electric vehicles and optimize its performance. Welcome you, sir.
Thank you, ma'am. Thank you very much for the introduction. Good evening, everyone. So I'm glad to see coordinators, researchers, academicians, and maybe some of the industry experts in one place, even it is online. So I'm really happy to meet all of you. So, and also I sincerely thank the FDP team for inviting me at this FDP and also to speak and to deliver a session in this FDP. So we all believe that today's research becomes tomorrow's knowledge. So therefore, I think this faculty development program on like emerging tech trends in optimal design of electrical vehicles and hydrogen fuel cell vehicles for sustainable future. So this faculty development program will showcase like various emerging technologies uh, that are going on in terms of electric vehicles or maybe energy storage. And these are all very important components in modern power systems, or maybe especially in power engineering. And also I can see from the schedule that this FDP has several speakers from various reputed academicians and also industry experts. So all of us will share our knowledge, and also we also encourage you to have some exchange of your ideas so that it will be useful for your research and also it will be useful for your teaching abilities. And I think I'm confident that all these faculty development programs and also all these presentations will be helpful for the participants, which will be immensely benefited from this FDP. And I ask all the participants that you make sure that this event will be as a gathering, like to have various researchers who is working in different areas, or even maybe in your area or maybe interdisciplinary area. So you can talk to them, and also you talk to the speakers, and you can ask them some research questions, and you can have some discussions, so which will be useful for your research as well as the teaching. So thank you very much for giving me this opportunity. So let me share my screen and let's go into our presentation. So can you see my screen, sir?
Yes, sir. Visible, sir.
Yes, ma'am. Thank you, ma'am. So today we'll see applications of these electric vehicles and also renewable energy and artificial intelligence, maybe some kind of optimization and energy storage, renewable energy. So we'll see all these applications of these, and then how these can be incorporated in the smart energy systems. So because nowadays everyone talking about like smart energy systems or smart grids or maybe hybrid power systems. So because incorporation of these electric vehicles and energy storage systems and also renewable energy, so our power system has now become a smart energy system or maybe hybrid power system. So let's see how these components can be modeled and you can achieve optimal performance by incorporating all these components in our traditional power system. So because we have originally traditional power system, now we incorporated various components and our system becomes smart. So let's see how you can optimize and how you can get better performance with the systems. So this is a brief outline of your presentation. So let's see importance of this renewable energy, electric vehicles, and various kinds of optimization techniques, and to modeling of wind power, solar power, or the load, or maybe modeling of battery storage, as well as electric vehicles. And then we'll see some problem formulations, and then we see with some results, and then we are going to conclude our session. So if you see, the first component in hybrid power system is a smart grid. Because whenever we have a smart grid, so we will be having various components in the smart grid, including these electric vehicles. So these electric vehicles, so we'll have, we can model in recent years, so electric vehicles can be modeled in various components in a hybrid power system or a smart grid. So in smart grid, apart from these electric vehicles, you will be having like wind energy, solar energy, or energy storage systems. And also you will have like various options for the customers. So customer options also we have, and we can increase the efficiency of our system. So apart from these components, you also have like various, you can say various entities or components in hybrid power system in smart grid. So because they are going to be useful for power quality improvement, or energy efficiency, maybe for generation or self-healing or market price. So all these are even importantly like demand response. So all these things can happen in a smart grid. So including these electric vehicles, because you can see like in smart grid, you can have like power storage, or maybe you will have like micro generation, like DG units, or you have like various modern components, and you will be having like smart meters. So including all these components, our system is now becoming hybrid system or a smart grid. So as you've seen, like in a smart grid, the major components are going to be renewable energy as well as electric vehicles and storage. Because nowadays everyone are talking about like renewable energy, because there are several reasons why we need renewable energy. Because the demand is growing rapidly, and the depletion of like natural resources like coal and oil, they are depleting very fast. So to overcome these things, so we need to meet this growing demand in an equitable and sustainable manner. So to get this, so we need to use this renewable energy. So need to efficiently and economically meet these energy demands. So we all moving towards renewable energy. So when you integrate large integration of renewable energy systems or renewable energy into the system, so as you know, the most of the renewable energy components are going to be like wind power and solar PV. So they are like vastly available, and their maintenance cost is very low. So that is the reason we use most wind power and solar power. But the problem is they are like spatially distributed. So they are small components and distributed into large places, and also inherently intermittent and unpredictable. So their nature is uncertain, and it is intermittent in nature. So to overcome these issues, so we need to have some kind of proper planning approach or planning methodology. So we need to plan this renewable energy into the system, so that your traditional power system it is going to get disturbed, but we need to reduce the disturbance. So because if you see, these output from these renewable energy sources is mostly depends on like wind speed, solar irradiation, and other climatic factors. But if you see all these factors, they are going to be uncertain and intermittent. So we cannot change the nature. So wind speed or wind irradiation, solar irradiation, you cannot control. So this uncertain behavior is going to create some challenges to our for planning and operational issues. So the system operator has to plan these renewable energy in an optimal way, so that this uncertain behavior can be minimized. So if you see this slide, you can see there are different types of solar energy or like renewable energy, including the wind energy, solar energy, or biomass, geothermal, or hydropower, tidal and wave energy. So these are all like renewable energy sources, non-conventional energy. But still, apart from this hydropower, so the power from other sources is very less. So we mostly depend on wind energy and solar energy, as they are have like more than almost 30% their energy share in the power generation. So you can see there are how the power is going to be generated from these renewable energy sources. Like wind is from wind energy, like wind velocity. Solar power is from solar irradiation. So these are how the power is going to be generated from the renewable energy. Now, when you incorporate all these components like renewable energy or electric vehicles, so our system is now become hybrid power system. So if you see in a hybrid power system, it has like various components. So you have various components in a hybrid power system, which includes like electric vehicles or charging stations or batteries, nothing but some kind of storage. And now you also have smart villages, smart cities, and as well as smart homes. So by incorporating all these components, so in a smart components, so our system is becoming hybrid power system, incorporating all these components. So now, as I said, in hybrid power system, you will be having various components, like you have renewable energy or bidirectional EV charging. Maybe they can be charged or discharged by using these electric vehicles. And also you will be having smart homes, smart buildings, and smart cities. So these are all modern hybrid components. So we need to integrate the system by incorporating all these components. So we need system integration of all these components. So when you have the system integration of all these components, we need to do some kind of optimization. So optimization of renewable energy production and usage. So you need to do optimization, how you can get optimal schedules so that your uncertainty can be reduced and it can be useful to the system as well as the customers. So if you see, we have like major renewable energy sources like wind and solar power. And the main problem is their uncertainties, because two main issues with renewable power are like variability and unpredictability. So these are the two main issues with wind power and solar power. But if you see all practical world problems, so to handle these variability and unpredictability, we need to have some kind of probabilistic models. So these probabilistic models, we can use it for the handling the uncertainties. So using the probabilistic models in a like mathematics, so we can use uncertainties, we can reduce the uncertainties. So, and also this random nature and integration of renewable power has posed a great challenge to the system operator, because previously the role of system operator is very easy when you have like thermal generators and hydro generators. But now in modern power system, we have like renewable energy, electric vehicles. So the role of system operator is now more challenge. So it is now we need to the system operator has to integrate the system, all these components, and he needs to handle the uncertainty related to these quantities. So the system operator role is very important in modern or hybrid power systems. So if you see the wind power, the wind energy is going to be uncertain in nature. But whereas in PV, solar PV, and variability, because solar PV power is going to be variable. If you see according to NERC studies, so it shows that solar PV installation can change their output by plus or minus 70% within the time frame of 2 to 10 seconds or 10 minutes. So this means in 10 minutes time, suppose if a solar plant is generating 100 megawatt, in 10 minutes time, the 100 megawatt power can change to only 30 megawatts. Or 100 megawatt power can change to 170 megawatt. So that means in 10 minutes time, so the variability is very high if you have by using this solar energy. So, and this is not one time, many times per day. So it is going to happen many times, because whenever suddenly you get the sunny weather, then suddenly it's going to be change the cloudy, or maybe it's going to be rainy. So the clouds are going to change suddenly. So within the 2 to 10 minutes time, the power output is going to be changed almost 70%. So this is nothing but the variability of solar energy is very high. So, and also wind power generation is also a variable. So we need to handle these variability and uncertainty related to this wind power and solar power. And also when you have this renewable energy into the system, so into the electricity markets, so this renewable power is not for free. So this renewable power, we need to have like two types of issues, in two ways you can sell this renewable energy. So one way is like non-market based approach. So that means you're not exactly entering into the market. You just go to the market and you sell your wind power and solar power at a fixed tariff. That means you already make a contract, so and you sell at the fixed tariff. So like preferential tariff, so you already defined the tariff. But whereas another one, market-based sale, here you can have like a electricity components and renewable energy certificate component. So you can have these two components. You can you can go to the market and you can sell the renewable energy, same like thermal generation. So as I said, you have two types of market, like non-market and market-based. So in some market practice one, what we do, we make the renewable power is schedulable or dispatchable. This means you can go to the market and you can bid in the market, and then you can get the price, that is marginal unit. If it is a marginal unit, you will get the price. But you should consider appropriate amount of reserves in its operational plan. Because if you go to the market, suppose you bid for 100 megawatt. But in real time, due to weather condition, you can able to generate only 70 megawatts. Then remaining 30 megawatts, you should have an option. You should have an reserve in operational plan. So in your planning, you must consider the 30 megawatts of reserve you should have. So then only you can go to the market and bid. Otherwise, so you should shift to the market practice too. So this is used mostly in North America. So in North America, many ISOs, they use this kind of market practice. So what they do, they can go to the market, they can bid, and they can set the price. Whereas in non-market based sale, or non-schedulable or non-dispatchable, what we are going to do is, the policy is to observe all wind power into the system and pay a fee established by the system operator, which is different from market clearing price. So this means you are not going to go into the market and bid the price, but what you do, you are just going to the market and you sell your power at a fixed tariff. So this kind of power is going to be used in all developing countries. So you observe all the wind power, all the solar power, and if the system operator sees some kind of problem, then he will disconnect your wind farm. So he can disconnect your solar farm, because if his system operator see if some problem is occurring because of your wind farm, you can just disconnect it. So this kind of policy is normally used in systems trying to increase their share of wind power in the generation portfolio. So all the developing countries, so they want to use this kind of market practice. So they are just price takers, and they do not affect your locational marginal prices, your LMPs. So they are not going to affect your LMP. Now coming to electric vehicles. So nowadays we see all the countries, they are moving towards electric vehicles, and also governments are giving a lot of subsidies to buy these electric vehicles because of several reasons. So the main reasons are listed here. So like availability of the fuel, because most of the countries, so we don't have fuel. We mostly depend on these Middle East countries for the fuel. So this is the availability of the fuel. And pollution, because if you have electric vehicles, there is no fuel, so you'll be having no emission. So the studies reveal that when you change all your vehicles by 100% electric vehicles, the CO2 emission is going to be reduced by 50%. That means only CO2 emission is 50% of CO2 emission is only by the vehicles. So even when you use renewable based charging, so means your wind based charging or solar based charging, so your carbon footprints are going to reduce drastically. So that is also another one. And the third one is a capital and maintenance cost. So electric vehicles have more capital cost, but the running cost is very less than IC vehicles. But if you use the solar based charging, even this running cost is going to be zero. So if you have solar energy based charging, so the capital cost is high, but the maintenance cost is very low with the electric vehicles. So if you see the comparison between electric vehicles and gasoline vehicles, maybe like petrol or diesel vehicles, so you don't have any tailpipe emissions, and the mileage range is now like plus or minus 100 miles. But this range is now increasing due to the advancement in energy storage technologies. And hours to charge, but previously we used to charge them hourly, but nowadays you can see because of the fast charging technologies, it can be charged in 30 minutes. And the like running cost is very low. It is 2 cents per mile, but whereas here it is more with the gasoline vehicles. Now, if you see these two vehicles, the electric vehicle and gasoline vehicle, if you keep them in a balance, so the cost of both the vehicles are going to be same if you run this electric vehicle at least for the 5 years. The minimum driving kilometers, if you run like 4 to 5 years, then the cost of both the vehicles are going to be same. Suppose if you say you are going to run this electric vehicle for 10 years, just say for 10 years. So for initial 4 to 5 years, so the cost is going to be same. Next 5 to 6 years, so you are going to get benefited with the electric vehicles. So of course, maybe due to the battery, if you need a battery replacement, it may get cost, but still the cost is going to be less or even at least not more than these gasoline vehicles. So if you use a gasoline vehicle, the cost is like 15.7 cents per mile, but electric vehicle 2.9 cents per mile. But if you use solar powered based electric vehicle, then it is going to be 0 cents per mile. So if you don't need to pay any cost, so if you use like solar power based electric vehicle. These are all different advantages with electric vehicle, but at the same time, if you incorporate these electric vehicles into the grid, into the power system, so you need to face some kind of challenges. So when you have large number of electric vehicles in the system, the challenges in electric vehicles are from grid point of view. So they are going to be intermittency or uncertainty, because EV load is intermittent. That means uncertain, because electric vehicle load, we don't know when my electric vehicle is going to be charged and when my electric vehicle is going to be discharged. So we don't charge electric vehicle at a fixed time. That means EV load is going to be changed. So EV load is intermittent, is uncertain. And also large penetration of renewable energy sources. So if you have large number of renewable energy, also it is going to create uncertainty or intermittency problem to the system. And also, if you have large uncertainty, so maintaining the grid stability for the grid operation is also one of the challenge if you have these electric vehicles. So these are the challenges with electric vehicles from the grid point of view. So because we talk about the system, so from the system point of view, so these are the challenges with electric vehicles. So energy and ancillary services markets, because when you have electric vehicles, so like we have like charging port, so you will be having like charging point, different charging points of electric vehicles. So when you have these different types of charging points, so this electric vehicle, all these charging points together, all these electric vehicles will become together an aggregator. So this aggregator, what he will do, because we cannot go to the market and bid, and we cannot participate with one electric vehicle. So what he will do, with an electric vehicle aggregator, he is going to participate in energy market as well as ancillary services market. This means some kind of supporting service like voltage support, reactive power support, or spinning reserve support. So those are nothing but ancillary services market. So this aggregator is going to have interaction with transmission system operator as well as a distribution system operator. So he is going to have distribution system and transmission system operator, and aggregator will have close relation with all these components and is going to make a good decision for electric vehicles. So for all these electric vehicles, the aggregator is going to take a good decision. So if you see ancillary services according to FERC, that is in America, you are like Federal Energy Regulatory Commission. So this FERC, this regulatory commission, has invented like they suggested like 6 types of ancillary services. They have like spinning reserve, supplemental reserve, reactive and voltage control, frequency response, energy imbalance, scheduling, system control, and dispatch. So these are all ancillary services. So they are going to support your system. So they are going to support your system so that your system is going to be have good voltage profile, good reactive power supply, and good power balance, and even the frequency response. So these ancillary services are going to be useful to handle any kind of uncertainty or any kind of imbalance occurred due to your sudden change in load or electric vehicles, or maybe the challenges occur with renewable energy sources. So relation between like energy and reserve services markets. So if you see, this is a suppose this is a single generator. What we will do, some portion of generation will go for the generation and load, and some we use for the regulating reserve. So like AGC control. So AGC control for regulating reserve you can use for some portion, and some portion we can use for the spinning reserve, and some portion you can use for the supplemental reserve. So these are called contingency reserve. If you have some kind of problem, maybe line problem, or you have some generation problem, then you use contingency reserve. And regulating reserve, spinning, and supplemental we all call like operating reserve. So these reserves are very much important when you have uncertain electric vehicles and uncertain power generation from renewable energy sources, because electric vehicle load is also uncertain and power generation from renewable energy sources also uncertain. So to handle these uncertainties, we need to go for reserves. So if you talk about this demand side management, so we have different types of demand side management systems. So basically, these demand side schemes are very important whenever you have lack of adequate spinning reserve margin. Suppose you don't have good spinning reserve, then we need to go for the demand side management, and shortage of tie-line capacity to make up the last generation. Suppose you lost some generation and you don't have good short tie-line capacity, so then we need to depend on these demand side response. So this is going to helping you to secure the grid. For grid security, so we need to use this. Like a single house can participate like a demand response. A big apartment building can participate in the demand response, or many electric vehicles. So all these electric vehicles can participate in the demand response. So these are all can be used like a flexible demand side management. So they are going to help you to overcome these problem due to lack of spinning reserve or last generation. So whenever you have demand side management, so suppose I am a customer, I cannot reduce my demand. So if I want to reduce my demand, I need to have some kind of benefit. So demand management options, you have tariff strategies. So if you participate in the demand response, your tariff is going to be maybe less. You have some kind of tariff plans, or you can use some kind of energy storage, or you can use some kind of mobile generation like distributed generation you can use. or you can use some kind of embedded generation. So different kinds of generation technologies you can use. So all these technologies can be useful for demand side management. So when you have, as I said, when you have energy and ancillary services, so what we need to do, you need to do simultaneous co-optimization. You need to do joint optimization. So you can have like joint optimization, then you can use them for optimal solution. So to get, these are going to use inherent relationship between energy and ancillary services, and you are going to get a best results. So you can see you give the energy offer, reactive power offer, reserve offer, you do optimization, and then you get the schedules, like how much is the energy, how much is your reactive power, how much is the reserve you are going to get. So these are going to recognize trade-off between energy and ancillary services. So they need some kind of trade-off. So that means not total energy from energy, or total from the reactive power, or total from the reserve. So it is a combination of, suppose you have one generator, so one generator can participate in all these components. It can participate in the energy, it can participate in the reactive power, it can participate in the reserve. So this means you can get most economical dispatch of all commodities in one source. So from one source, you can get all the components. That means in one components, you can get most economical dispatch. So you can receive most economical dispatch if you do your joint optimization. So now again, I said, whenever you have electric vehicles, so because nowadays most of the researchers, they are working in this renewable energy. So and also electric vehicles. So when you have these electric vehicles, so your question is, what optimization problem I can do with electric vehicles? So you can think of doing many kind of research, so various research activities with electric vehicles. So like optimal location and sizing of electric vehicle charging stations, because nowadays most of the researchers, they are working on this topic. So this is optimal location and sizing, because previously when we don't have these electric vehicles, we used to study optimal location and sizing of fax devices or shunt capacitor banks, or we used to do some kind of optimization related to so some kind of optimization which is related to electric vehicle charging stations, like D-STATCOM location, DG's location, or you can do some kind of optimization like this. And also you can have benefit maximization of parking lot owner. So whenever you have parking lot, so because parking lot he cannot do by himself. So parking lot owner, so he cannot do it for the free. So same like we have gas station or petrol pump. So we cannot do it for the free. So he must have some kind of benefit. So you can make a problem formulation so that the benefit can be maximum, be increased with the parking lot owner, so that you can do it. And also maximize aggregator profit. So suppose I said we have aggregator, because one electric vehicle cannot participate in the market. So what we can do, so aggregator can increase its profit. So you can do some kind of work in terms of aggregator, and also minimize EV charging cost, because the main aim is we have to reduce the cost. So EV charging cost, how you can reduce the EV charging cost, that you can also formulate a problem. Or you can also make minimize total operating cost in the system. You can have total cost, you can think of total cost, and then you can minimize, you can do some kind of optimization. And also those who studied in power system deregulation, you may be thinking about like how to maximize your revenue, or maybe social welfare. So you can think of doing some problem maximizing revenue or social welfare of grid operator. So for the grid operator, how you can maximize your revenue and social welfare for the grid operator. So you can think about this. So when you see the first problem, like optimal location and sizing of electric vehicle charging station, I will show you one small picture. So you can think of doing some kind of problem like this, like in a distribution system, you can see optimal network reconfiguration, or you can see optimal allocation of renewable energy based distribution systems, like distributed generation, or you can talk about allocation of DSATCOM, because in a distributed system, so for reactive power management, you can use DSATCOMs, or allocation of electric vehicle charging station, because now we have electric vehicles. So whenever we have electric vehicles, so we need to talk about electric vehicle charging stations. So where to install the charging station? So that is optimal allocation of electric vehicle charging stations. So you can think about how you can do optimal allocating electric vehicle charging station. So if you see this combination of these problems, you can do simultaneous allocation of DGs, electric vehicle charging station with the network reconfiguration. So this kind of optimization can be done. Or you see this combination, it is a simultaneous allocation of DGs, DSATCOMs, and electric vehicle charging station, or a combination of all the four can also be done. So this kind of optimization can you can think and you can solve some kind of problems related to electric vehicle or electric vehicle charging stations. Now, if you see how you can model these electric vehicles in the system, so this is a power grid. From the power grid, you will be having the charging station. So maybe you use some microgrid energy systems, or from there you can see charging piles. So these are the charging piles. From the charging piles, your electric vehicle, so our electric vehicle users, they can use charging or maybe discharging. So from this, you can see the electric vehicle can charge as well as the discharge. So you can see here, electric vehicles will play two roles, like when they plug in the system, they act like a loads or maybe generators. So during the charging, they act like a loads, and during the discharging, they can act like a generators. So, so you can use these two options to model the electric vehicle in the power system. So you can use two types of modelings. So for the electric vehicle, that is charging as well as a discharging. So now talking about modeling, exact modeling. So at a particular time, so we don't know our electric vehicle is a charging or discharging. So the instantaneous charging status of a battery system in an electric vehicle. So you can charge this electric vehicle. So you can model, so by using like this equation. So power output, or maybe charging or discharging power of an electric vehicle at a particular time. So you can determine by considering maximum capacity of electric vehicle minus exponential function plus initial. So how much, what is your current status of your battery before the time? So what is the initial status and what is the current status? So it is exponential function. Maybe it is charging or discharging. So like this, you can model the power from electric vehicles. So as I said, whenever you have electric vehicles, so there is electric vehicle charging station load is uncertain. So whenever there is uncertainty, so you need to use some kind of probabilistic approaches of uncertain modeling. So to model your uncertainty, you need to use some kind of probabilistic modeling. So this probabilistic model may be divided into like numerical approach based modeling or analytical approach based modeling. So in numerical approach, what we do, we use some kind of Monte Carlo simulation. So in Monte Carlo simulation, again, you have sequential, non-sequential, and pseudo-sequential based Monte Carlo simulation. But the problem with Monte Carlo simulation is, so they need a large number of samples data. So the size of the sample data is large, and also to process the sample data, you need you need to have more time. So the time is one problem, and also getting the large data is also one problem. So to overcome this issue, so instead of numerical approaches, we can go ahead for the analytical approaches. This analytical approach is based on two models, like based on probability density function approximation, PDF, probability density function, or maybe based on the linearization. So these two are not very much accurate when compared to Monte Carlo simulation, but they are going to be approximately the similar solution compared to Monte Carlo simulation, and they are going to take less time when compared to this Monte Carlo simulation. And you don't need a full set of data. You can get some kind of approximation or linearization. So in recent years, when you don't have much time and when you don't have a large data set, you can use analytical based approaches to model this probabilistic based uncertainty. Now, compared to now coming to modeling of electric vehicle. So to model the uncertainty of these electric vehicles, so we have to use normal distribution function. So this normal distribution function can be modeled like normal. So based on the time of your electric vehicle charging as well as the discharging. Suppose nowadays, as I said, the main problem with electric vehicle is a charging time. Previously, it used hours to charge. But nowadays, due to advanced charging technologies, you can also use like dynamic charging electric vehicle. So this is the bus is traveling under this track. So you can see this is a power track. So this bus is a online electric vehicle. So it's a campus shuttle bus which is developed in Korea. So in Korea, you have this bus. So where the track is different for the bus. So here the bus, when your bus traveling on this track, so the bus can charge automatically. So it is a dynamic charging. So there is no need to bus to charge separately after its running time. So you can charge this bus whenever it is traveling on the road itself. So this kind of dynamic charging technologies are going to take place in more advantages and more research developments so that you can reduce the charging time. And then, but of course, the maintaining this power track is costly, but still, once you have power track is built, so it can be used for many years. So now, after you have electric vehicles, so you also need to model electric vehicle charging station. So these pictures, the left side and the right side, they show a typical electric vehicle charging station. So this is a rental service provider, and this is a Hyundai EV station. So this is the largest and fastest charging station with capacity in Korea. So here, this is a typical electric vehicle charging station. But we also need to model these electric vehicle charging stations because we need to model the load of an power system. So when you want to model the load, so you need to have power demand for the electric vehicle charging station. So the load model of electric vehicle charging station, so you can see the demand of the power demand of electric vehicle charging station, so which depends on how many electric vehicles they are charging, so grid to vehicle, and then what is the charging efficiency, what is the charging rate, minus how many electric vehicles they are discharging. So vehicle to grid, and then discharging efficiency, and discharging rate. So charging minus discharging, you are going to get power demand of an electric vehicle charging station. So this is how you can model the load demand of electric vehicle charging station, that is power demand of electric vehicle charging station. So PD EVS is you can determine by considering charging and discharging status of electric vehicle. So now we also need to model the electric vehicle load modeling, because when you use voltages, what exactly, suppose let's say our house we use voltage is 230 volts, but if you check exactly, the voltages are not 230 volts, it may be 210 volts, maybe even 200 volts. So that means we need to have the exact load modeling so that you can get the more power. So what we promise to have. So here the exponential load model is selected for modeling the loads of power system as well as electric vehicle charging station. If you see the power demand of a electric vehicle, this is a total power demand and power demand with electric vehicle charging station. So you can model the power demand so by considering voltage dependent load modeling. So by considering exponential load model. So NP and NQ, they represents like by considering load modeling coefficients, exponential coefficients. So again, when you talk about modeling of wind energy systems, when you talk about this wind energy, so we need to model renewable energy by considering wind energy systems. So modeling of wind energy system will have each power plant. So they have power is determined by considering wind velocity and power demand. So based on your wind velocity, the power output is going to be calculated. So based on your wind speed, the power output is going to be calculated here. So here we use like a linear function. So here we are using like a linear function, but when you have instead of this linear function, you can also model the more accurate wind modeling by considering quadratic or cubic function. So you can have like cubic function. So you can use quadratic function and also you can use a cubic function like this. So the power output is directly proportional to velocity cube. In the previous expression is we have used the linear function. So it's directly proportional to wind velocity. But here is directly proportional to wind cube of the wind velocity. So you can see it's a V cube and V cube. So this is going to get more accurate solution when you model a power output from wind energy generator as a cubic relationship. So now when you talk about the wind speed and probability density function, so the wind speed is modeled by considering Weibull distribution function, and wind power is also can be modeled by in a continuous range as well as a discrete probability range. So you can have continuous probability as well as a first discrete and second discrete probability. So you can have these two quantities, again these two problems. And also, as I said, you need to also have the wind forecast uncertainty model, like load forecast, because future load is also uncertain at a particular time. So you cannot guarantee the future load at this time. So this is your load demand. So it's not guaranteed. So future load is also uncertain at any given time. So we need to model this load forecast by considering normal probability density function. So this probability density function at any uncertain load, you can model like this. So this is even useful for the electric vehicle load forecasting as well as a normal load forecast. So you can use this expression for normal load forecast as well as a electric vehicle load forecast. And Another component of modern power system is a solar energy system. So when you have solar energy system, the power output, solar irradiation, so G, so the power output can be calculated as a function of G. So here we neglected the temperature of the solar PV cell, but after neglecting the temperature, so the power output can be calculated by considering this solar irradiation. So again, if you see this solar PV model, solar PV generator with battery storage, so you will be having a PV generator. So from the PV generator, you extract the power is like PPV, and PU is some kind of spillage power, because you cannot extract 100% of power from this PV cell, so our PV generator. So some power is going to be spillage, and you can also use the battery combination. So you can charge or discharge power from this battery, and this combination is going to get power at the particular bus, because in a power system point of view, we are not much concentrate about all this power, PPV or PU or PV. We concentrate on PS. That means what amount of power you are injecting to the power system at a particular bus. So this is like more important for the power system engineer. So how much power you are injecting at a particular bus. So the PS is more important factor, which you can calculate by considering solar power, battery power, and spillage power. So again, as I said, the modeling of solar uncertainty is also uncertain. So we need to consider the uncertainty related to this solar PV. So this uncertainty you can model or you can consider by considering viable function, so which can be modeled by using this function. So it includes hourly solar irradiation by considering bimodal distribution function. So again, you can also model the battery. You can model the battery like a battery energy storage system, which includes battery charging power as well as a discharging power. So the state of charge of a particular battery you can determine by considering the charge at a particular time divided by maximum charging status of the system of the battery. So now if you talk about how you can determine the charging of a battery, so it depends on initial state of charge of the battery and how much power battery is charged, and then how much power is discharged from the battery. So if you calculate these powers, the remaining charge of a battery at a particular time can be determined. So this is how you can also model the battery energy storage system in a power system. Now, when you have all these components in a system, your task is now how you can optimize all these components in a modern power system. So if you see, now let's see what is like optimization. So if you talk about optimization, we can see optimization is nothing but some kind of mathematics where you can determine finding the maxima or minima subjected to various constraints. So these optimization problems are not single problem. So they classify into different categories based on constraints, maybe nature of variables, maybe based on your equations involved, or nature of your variable, deterministic or stochastic variables. So what is your nature of the design variables? And also, how many objective functions do you have? So based on this, the objective function, the optimization is going to change. So now talking about classification of variables. So it can be classified into integer programming problem, or it may be classified into real valued problem. So based on your design variables. So again, the problem optimization can also change to like a deterministic programming problem or stochastic programming. So if you say deterministic, previously our traditional power system, we just have thermal generator, hydro generator. So in that case, your design variables are deterministic. So they don't change with time. But whereas stochastic programming, so when you have wind power, solar power, electric vehicles, so then your problem is now become probabilistic model or non-deterministic or stochastic model. So then you need to use some kind of optimization technique related to the stochastic programming. So again, based on your number of objective function, whether you have one objective or multiple objectives, so you can use, so based on that, you can use a single objective optimization or multi-objective optimization. So if you have two or more objectives, then you can use single or multiple objectives. So if you see various types of optimization techniques, you can broadly classify into like a classical optimization, like conventional optimization and non-conventional optimization. And you can see programming like mathematical programming, calculus, networks. In non-conventional, you can say it is a meta-heuristic algorithms. So nowadays we use meta-heuristic algorithms due to several reasons. So because we have like various limitations with conventional techniques, like in conventional techniques, we use gradient-based optimization. That means we are linearizing system objectives and constraints. So we use some kind of linearization in conventional optimization. But whereas practical systems, so they are highly nonlinear, multimodal, and non-convex optimization problem. So they are going to be non-convex in system. So in that case, what we do, we use some kind of meta-heuristic algorithms, like we use evolutionary algorithms, or physics-based, or swarm-based, or human-based algorithms. So you have different types of meta-heuristic algorithms which we can use in recent years for solving our optimization problem. So when you have evolutionary algorithms, the main advantage is like they can handle nonlinear multimodal objective functions. You can get the system is independent. So whatever the system size is not a problem with the have evolutionary algorithms, free from complex derivatives and insensitive to initial values. So we don't need to worry about the initial values. So if you see, there are different types of evolutionary algorithms. So the basic ones are like genetic algorithms or particle optimization. So they all belongs to these evolutionary algorithms. So basic evolution cycle in all these algorithms are like we have present generation, and then we use some kind of selection criteria. Then we are going to select some parents based on the selection criteria. Then we use some kind of crossover and mutation operations. Then we are going to get new generation, and we are going to replace the generation. We get again present generation. So this cycle is going to be repeated till we get a best solution. So this is the basic evolution cycle in most of the evolutionary algorithms. Now, coming to multi-objective optimization, as I said, when you have more than one objective functions, so we can use this multi-objective optimization. So what we do here, we have two or more objectives, and we don't have no unique solution, but we need to find trade-off solution. So, and also it requires good level of high-level information or your experience, so to determine this high-level information. So let's see one small example to buy a car. Suppose you want to buy a car. So suppose if you pay like maybe some like 200K. So in that car, you get a one old car, maybe less comfort car. You can see if you pay some 200K, you get only 40% comfort. But if you pay 1000K, so if you pay like 1000K, you get a car with 90% comfort. So there are two extreme points. So one is like less money but less comfort. This is more money but more comfort. So these two are the two extreme points in multi-objective optimization. But in between, you exist like many solutions like this. So you can see there are different solutions exist in case of multi-objective optimization. So you mark this curve and you choose the best solution which is going to suitable for you. So not these extreme points, but based on, suppose you see here, you increase your money a little bit, but your comfort you are increasing almost by 20%. That means you change your cost by only 5%, but you increase your comfort by 20%. And even you see, you increase your cost by maybe 10%, but your comfort is increased by almost 70% or 80%. So based on this, you need to determine so which point you are going to choose. You are going to choose this car or this car or this car. So you need to determine a suitable price. So for buying a new car, you decide based on various factors like how much finance you have available, how much distance you travel every day, and how many passengers, what is the fuel consumption, what is physical health, what is social status, what is the road condition. So you need all these answers. Based on this, you find one best car for you. So this is how you can determine multi-objective optimization. So in multi-objective optimization, what you do, you find a solution. So you minimize some objectives, F1 and F2. So you have many objectives. We use some kind of optimization algorithm, and you determine the best trade-off solution. And then you use some decision-making solution. You decide, so based on your knowledge, and then you will decide which one you are going to buy. So the final solution. So it depends on your decision making. So you make your decision and then you determine the final solution. So there are different types of multi-objective optimization algorithms available. So you can see there are many algorithms like NSGA2 or multi-objective evolution algorithms, strength Pareto evolution algorithms. There are many algorithms available in the literature. So again, you can determine best compromise solution by considering multiple objectives, multiple objective functions. And let's see one small problem where you can use the single objective optimization. So by considering single objective optimization, how you can solve your problem. So now let's see, you have different objectives. Let's say you want to reduce your cost and you minimize your mean adjustment cost in the real time, and how you can reduce uncertain nature of wind power and load forecast. So you can reduce all these components, all this work, and then you can determine how your work is going to be useful to reduce these deviations. So one model you can consider like demand is inelastic to the price. So another model you can find demand is elastic to the price. So these are the two models you can develop for the wind power. So like the cost of the power, thermal generation, wind generation, and the deviation. So that means what is your uncertainty. So if you have some uncertainty, that we need to reduce. So again, cost of the demand, if you have the social welfare, you can use the cost of the demand minus cost of your wind power, thermal power, wind power, and power deviation. So these are objectives, and we need to consider like real-time optimal power flow and deterministic based real-time optimal power flow, because the wind power is going to change. So maybe wind power is going to vary in epsilon percentage. Maybe you can say 5% uncertainty or 10% uncertainty. So then you do your real-time optimization. So this is a proposed solution methodology. You consider system data, load forecast data, wind forecast, or solar forecast. And then you do this optimization by considering some kind of chromosomes and the population criteria. And then you can see real-time schedule you can determine by considering two-point estimate method. This is for uncertainty handling, and then use deterministic OPF and real-time schedules. So you can handle this kind of determination of real-time schedules you can determine. And as I said, every objective function, you must have some kind of constraints. So these are different constraints you can handle, like wind generator constraint, thermal generator, power balance, transformer, or security constraints. So you can handle all these constraints, and then you can determine best values for your objective function. So if you see case studies and attribute 30% system, so you have like when you don't have any uncertainty, no uncertainty, in that case, the cost is 955. But whereas if you consider 20% uncertainty or 30% uncertainty, the cost is going to be increased. So based on your uncertainty level. So if you use 20% or 10% or 5%, because if you see load is a 5% variability, then in that case, you can see the total cost is going to be increased. So this is how you can increase the cost of your total power generation. And also you can have different combinations like 20% uncertainty in the wind and 5% in the load, or 30% in the wind or 5% in the load. You can see the cost difference. So the cost is increasing with the increase in uncertainty percentage. So you can, the objectives of this function is like you can consider like best fit generation, and then you can determine best fit schedules so that you can use the probabilistic models to find different operating time scenarios. Similarly, you can also see like second problem. So let's see based on multi-objective based optimization. Here what we do, we consider the one objective function by considering cost of the thermal generation, wind power, solar power, batteries, electric vehicles, and as well as these uncertainty. So real time, the cost of real time for the deviation power, that means uncertainty power. So each component like cost of thermal power, wind power, solar power is calculated by using these mathematical expressions. Similarly, the battery power, electric vehicle can be calculated by using these expressions. And mean adjustment cost, that is uncertainty cost. So this can be determined by considering day ahead, what is the cost, real time, what is the cost. So by using some expression, some kind of equation, mathematical expression. Again, objective, one objective is like a cost minimization. We have to minimize operating cost. The second objective is like we have to minimize the risk level. So this risk level, you can, because when you add more wind power, more solar power, more electric vehicles into the system risk will be high. So we need to minimize the risk. So this kind of fuzzy approach also can be used to minimize the risk. And also another approach, like you can use CVAR, conditional value at risk. So this is also one more index which you can use for the risk minimization. For the risk also, you can use this kind of minimization function to minimize the risk in the system. So this is how you can calculate the CVAR. So where it includes combination uncertainty, like wind uncertainty, solar uncertainty, and electric vehicle uncertainty. So these objectives, two objectives, you can optimize by considering various equality and inequality constraints. So these constraints will have, we have like different types of equality and inequality constraints. So these are different constraints we can handle with the by considering two objective functions. So whenever we have two objectives, so we need to optimize by considering non-dominated sorting based genetic algorithm that is called NSGA2. So we can use NSGA2 algorithm. So this is one of the multi-objective optimization algorithm. So you can see here 2 objective functions and 2 fitness, and then you are going to do optimization related by using non-dominated sorting based genetic algorithm, that is NSGA2. At the end, we are going to use fuzzy approach to determine best compromise solution. So by using this fuzzy approach, we can determine the best solution. And coming to simulation results, so here in this study, you can see 3 case studies are determined by considering only cost, only risk, and cost and risk minimization simultaneously. So case 1 and case 2 are single objectives, and case 3 is a multi-objective. So coming to case 1, case 2, and case 3, case 1, we use only cost minimization, here risk minimization, and here we use cost and the risk together. So here the cost is less, but the risk is high. Here risk is less, but cost is high. So that's why we use in case 3, so compromisation between cost as well as the risk objectives. So this is a voltage profile which we observed for 3 systems. Like you can see, so voltage is very less in case 1, high in case 2, but in case 3, the voltage is a compromise. It's not very high or not very low. It's a best or compromise voltage profile in the system. So here, as I said, here 2 objectives. One objective is a cost minimization. Other objective is a risk index minimization. So when you do cost and the risk minimization objectives, you get some curve like this. This curve is called Pareto optimal front. So, but if you see these dots, each dot represents each small circle. So it represents one single solution. So in this plot, you have 50 solutions. So all these 50 solutions are solutions for your work, but you need to decide the best solution based on your experience. So, or based on your fuzzy min-max approach. So this is one solution where you can use to determine best compromise solution. Now coming to conclusions. So for this work, so we have modeled various components of wind generators, solar systems, batteries, and electric vehicles. And we have seen different types of optimization techniques to model these electric vehicles, batteries, and storages. And also we have seen like multi-objective optimization, where you have cost minimization and the risk minimization, so that you can have both objectives can be determined, solved simultaneously, and then you can have best compromise solution. Because one objective is a cost is obvious objective. The other objective is like a risk, because whenever you introduce more wind, more velocity, like more solar, more electric vehicle, system is going to have more risk. So we need to increase the security of the system. So other objective, you can minimize the risk or increase the security of the system. So those are considered like a different objectives when you have large number of electric vehicles and energy, like renewable energy systems. So these are some references we used for doing this work. And at the end, so you can also see there is presently I am editing one book. So the book will be published in Green Energy and Technology. It's a Springer book series. So Green Energy and Technology book series. So presently I'm having editor for this book. So the book title is like Next Generation Green Energy Technologies for Sustainable Development. So if some of you or your students are interested to publish a book chapter, any topic, we don't have any fixed topic for this book. So any topic related to the green energy or electric vehicles, or maybe wind energy, solar energy, some kind of uh, energy generation technologies for sustainable development. So if you are doing any work so related to this topic, so you can contact me. You can send any chapter to this book. So there is this each chapter of this book will be indexed in the Scopus, and there is no publication fee for this. So each chapter will be indexed in Scopus, SCI, and EI Compound X. So these are the indexings available for this book, and no publication fee. And the deadline for chapter submission is like March 31st. So if somebody interested, maybe you or your students, so you can send a chapter to this book. So this book publisher is a Springer. And thank you for your patience listening. So you can contact if you want to submit your book or any questions, so you can contact me to this email. It's surender@wc.ac.kr. So if you have any questions, so I'll stop now my presentation. So if you have any questions, so you can please unmute yourself and then you can ask.
Thank you, sir. Participants, if you have any queries, please write it in the chat box. If you have any queries, write it in the chat box, please.
Yes. So if you have any questions, so you can unmute yourself and you can ask, or you can also type in the chat box.
Sir.
Thank you.
Yes, sir. Please tell me, sir.
Please.
Yes,
please.
sir. I want to know about the recent advancement in ultra or super capacitors, sir. Actually, sir, the technologies that is used is almost 10, 20, 30 years past. So, is there any recent advancement in ultra or super capacitors, sir?
Yes, sir. So not exactly recent technologies, sir, but you can use ultra supercapacitor or like supercapacitors. You can combine the supercapacitor with another storage technologies. So that you can combine the advantages of both supercapacitors as well as maybe if you combine with the fuel cell or maybe with the battery. So you can combination of these hybrid storage technologies. So you can have more advantages because some storage technology has high energy density and high power density. So you can combine 2 or 3 energy storages and then you can make a hybrid storage technology. So it will be useful because nowadays people are not working to improve the single capacity of the supercapacitors, but in a combination like supercapacitors and you can supercapacitor and batteries you can have good combination, and supercapacitor and the fuel cell you can have the good combination, and then you can have good storage. So you can have hybrid energy storage technologies by combining 1 or 2 or like 2 or 3 individual storage technologies.
Okay, thanks, sir. Thanks.
Yes, thank you.
Thank you. Thank you, Pradeep sir, for your active participation. Is there any query? Is there any query? Please ask. Okay, sir. I think no queries are there.
Okay, ma'am. So then, yeah. Okay.
Okay,
Thank you,
sir.
ma'am.
Okay.
Thank you, sir. So it's my pleasure to have here. So
It's
I'm
our pleasure.
really happy to meet.
It's our honor, sir. So we are privileged to have you among us today, and we thank you for taking time out for your busy schedules to extend your support, sir. Thank you very much, sir.
Yeah, thank you, ma'am. Thank you, sir. So thank you, everyone.
No, thank you very much, Sudhir sir. Nice presentation. I think
Yes,
you are
thank you.
strong in publications and your work is so impressive. Thank you very much, sir.
Yes,
for
sir.
your,
Thank you, sir. Thank you very much, sir.